Alright, what's going on, everybody? This video we're going to look at limits and continuity of multivariable functions. So let's go ahead and get started. So let's take a look at the definition. So definition, let f be a function of two variables whose domain D includes points arbitrarily close to AB. Then we say that the limit of f of xy as xy approaches some point AB is L, and we write this. This is how we would write the limit. The limit of f of xy as xy approaches some point AB is equal to L if for every number epsilon greater than 0 there is a corresponding number delta greater than 0, such that if xy is in the domain and the square root of x minus a squared plus y minus b squared, the square root of that is between 0 and delta, then the absolute value of f of xy minus L is less than epsilon. Alright, so that's the definition. We don't really want to work problems like this. We will do one using this in the video, but I'll show you some other stuff too. So, and then some other notations for the limits would be this and this. I will use this notation throughout the video. So, but these are other notations here. So I'm going to erase this so I can have some room. I want to kind of give you a graphical representation of what we were talking about there. So let's look at a drawing. All right. So if I've got x, y, and I've got some point here, okay? This is some point AB. And so we have like a little circle here around that point. And this radius here, that's delta. I know it's kind of crammed in there, but that's delta, okay? This is your point AB. Okay, so if we have an interval over here, we'll say this is L, and then we've got L plus epsilon, L minus epsilon. Okay, so if we have any small interval, which is L minus epsilon to L plus epsilon, is given around L, then we have a disk over here with center AB. So that point there, AB is the center, and the radius is delta. All right. So F maps all the points in this disk into this interval here, except possibly at the point AB. So in other words, if I had a point, say like here, I had this point XY. Well, that point, we could map it over here, okay? And that's what it's talking about. All right. All right, so what can we do to show that a limit does not exist? Well, you remember in single variable calculus, okay? Remember in there, if we could show that the limit as x approaches some number a from the right does not equal the limit as x approaches some number a from the left, then that meant the limit does not exist, okay? All right, so what we have here showing that a limit does not exist. So if the limit f of xy as xy approaches AB is equal to L1 along a path C1. Okay, I'll talk about that a little more in a minute. And the limit of f of xy as xy approaches AB is equal to L2 along a path C2, where L1 does not equal L2, then this limit does not exist. So if we can show that the limit from different paths are not the same, then that means the limit does not exist. All right. So let's look at it at this example, and I'll explain more about those paths as we're working through the examples. All right. So we've got the limit of x squared minus y squared over x squared plus y squared as xy approaches 0, 0, and we want to show that this limit does not exist. Okay. All right. So what we have here, if we look at this, okay. So here's our point 0, 0. We got x, y, and we want to come into this point from different paths. All right. So we can come into this point along the x-axis. You see that? Along the x-axis. We can come along the y-axis. We can come along the line. So if we had this line here, y equals x, we could come into that point from the line y equals x. Okay? And I'm gonna do a little more of this in another example where we do come in along the line y equal x. But there's an infinite number of paths that we can come into this point. Okay? So and you'll see more of that as we work through the examples. Okay? All right. So the first thing, let's try coming in along the path, or well, along the x-axis. Okay? So if we want to come in along the x-axis, well, what does that mean? That means y is equal to 0, right? Because anytime we're moving along the x-axis, the y value is 0. No matter what point we're at on the x-axis, your y value is 0. So this is going to be the limit as x, y. Now what is y? Y is 0. Okay? As that approaches the point 0, 0 of x squared minus 0 squared, okay, because remember y is 0, over x squared plus 0 squared. And so this is equal to the limit as, now we're just in terms of x now, so we're going to take the limit as x goes to 0 of x squared over x squared, which is the limit as x goes to 0 of 1, which equals 1. Okay, so that's the limit coming in along the x-axis. All right, now let's come in along the y-axis. So if we come in along the y-axis like this, that means what? That means our x value is equal to 0, right? So we've got the limit as, now what's 0? X is 0. That's a 0y approaches 0, 0 of, all right, so let's plug this in. We've got 0 squared minus y squared over 0 squared plus y squared. And that's the limit as, now we're just going to be in terms of y, so that's y approaches 0 of negative y squared over y squared. That's a 2 there. And that equals the limit as y goes to 0 of what? Of -1. And so this limit is -1. And so these two limits are not the same. They don't equal each other. So the limit does not exist. And that's what they asked us to do, to show that that limit does not exist. So we've shown these two values here are different. All right. All right, so let's look at this limit. They want to know, does it exist? They did not ask us to show that this limit does not exist. They just asked us does it exist? All right, so we're going to do the same thing. We're going to come along the x-axis, we're going to come along the y-axis, and hopefully, keep our fingers crossed, hopefully we'll get two different answers. I don't know. Let's look. All right, so let's come along the x-axis. All right, so if we come along the x-axis, that means y is equal to 0. I don't know if you need me to keep drawing this, but I guess I'll draw it on this one. Okay, we're coming along the x-axis, and so y equals 0. All right, so we get the limit as x0 approaches 0, 0 of, what is that? X times 0. We're plugging the 0 in for y because y is 0 along the x-axis. X squared plus 0 squared, which that is the limit. And you can see we're just in terms of x. X goes to 0 of 0 over x squared, which is the limit as x goes to 0 of 0, which is 0. All right, so the limit along the x-axis is 0. Now, let's come in along the y-axis. All right, so that's the let me change colors back. So that's the limit as 0y goes to 0, 0. All right, coming in along the y-axis. Well, let me do this along y-axis. And that means x equals 0. So that's the limit as 0y approaches 0, 0 of what? 0 times y over 0 squared plus y squared. And so this is the limit as y goes to 0 of what? 0 over y squared, which equals the limit as y goes to 0 of 0, which equals 0. Okay, so we got the same thing. So does that mean that they're equal? No. That does not mean that it doesn't, well, yeah, let me say that again. Yes, they're both equal, but does that mean that the limit is equal to 0, that this limit exists and it's equal to 0? No. Okay? It has to be the same coming in from every path. All right? Coming in from every path. So now, let's look at this. Let's look at the line. Let's look at the line y equal x. And let's come in from that line, from the line y equal x. All right. All right, so what if we do along y equal x? So what is that going to be? That's going to be the limit. All right, now let's look at this for a second. So y is equal to x. So x, and I'm replacing y with the x, and that's going to 0, 0. Okay, and now let's just write this: x, y over x squared plus y squared. All I did, I just copied this down here so we could look at it. Okay. All right. So what we're doing here is we're replacing the y values with x. All right. So this is going to be x times x over x squared plus x squared. So I replace the y values with x. So this is going to be the limit as, now we're just in terms of x. And so this is going to be x squared over 2x squared, which is the limit as x goes to 0 of 1/2, which that limit is 1/2. And so you can see not the same. So the limit does not exist because, see, we've shown two different values, and and that value is different than that one also. So we showed that that limit does not exist. All right. See, it's not really that bad. Some of them can get kind of like we don't like them. But, anyway. All right, so let's look at this one. All right. So we've got xy squared, x squared plus y to the fourth. We want to know, does this exist? All right. So, there's some things that we can look at here. We can save some time. So to save some time, well, of course, we can go along the x-axis, the y-axis, and then along the line y equal x. Okay. Now, let's just think about that for a minute. All right. So to save me one thing, so notice up here in this one, I did along the x-axis, the y-axis, and then along the line y equal x. So save a little bit of time. Let's go along the line y equals mx. Okay. So what does that do? Well, just to give you a note here, this is any line through the origin that is not the y-axis. All right, so think about it. That's any line going through the origin, including the line y equal x if m is 1, and this is going through the line y equals 2x, 3x, y equals negative 0.52x. Okay, whatever m is. M can be whatever. All right. And then also, what if m is 0? If m is 0, that's giving us the line y equals 0, which is what? That's the x-axis. Okay? All right. So let's look at this problem. So this is going to be the limit as x. Now, y is equal to mx. So I'm going to replace y with mx, and that goes to 0, 0. And that's x times mx squared. I'm taking the mx and I'm plugging it in for y. And that's over x squared plus mx to the fourth, which this is the limit as what? Well, now I'm just all in terms of x. So I've got x goes to 0 of what? of mx cubed over x squared plus m to the fourth x to the fourth. All right. And so this is going to give me the limit as x goes to 0 of, now let's see what we got here. We got mx over 1 plus m to the fourth x squared. So I just divided each of these by x squared. So that left me with the x, that went to 1, and that went to x squared. All right. All right, so now this is the limit as x goes to 0. Well, I'm sorry. No, it's not. It's not the limit. We're going to plug 0 in now. I'm going to do it up here. I think I got enough room. That's m times 0 over, what is that? 1 plus m to the fourth times 0 squared, which is 0. That's equal to 0. So that's including the x-axis and any line coming through the origin. We're going to get 0. All right. All right, now let's look along the y-axis. And that's when x is equal to 0. All right, so that's going to be the limit 0, 0y as it goes to 0, 0. And so that is going to be 0 times y squared over 0 squared plus y to the fourth, which is equal to the limit as y goes to 0. And that's just going to be what? That's going to be 0 over y to the fourth, which is the limit as y goes to 0 of 0, which is 0. All right. So we've shown that along the y-axis and actually along the x-axis that it approaches 0, and any line coming through the origin, through that point 0, 0, is 0. And actually, I wrote the problem wrong. I mean, it's not going to affect what we did. See here how I wrote AB? That should be 0, 0. All right. There we go. All right. So anyway, I mean, we're going to 0, 0. That's how we're working the problem. All right. So does that mean the limit exists? Because we showed the x-axis, the y-axis, and any line coming in equals 0. So surely that has to mean this limit exists and it equals 0. Well, no, that's not the case, because it has to be equal along every path. Okay? So now let's do this. What about along the path x equal y squared? Okay, you see what I'm telling you? There's an infinite number of paths coming into that point. Yeah, we could do y equals x squared, but I think if we do y equal x squared, well, I think we might end up with 0 again, and then we would go to this one. But doing y equal x squared, x equal y squared, they're going to be it's going to be the same on how you work them. So let's do this one, x equal y squared. So this is the limit as xy, but what is x? X is y squared that goes to 0, 0. All right, so let's write this down. xy squared over, what was it? X squared plus y to the fourth. I just wrote this down again. Okay, so we can look at it when we're plugging everything in. So in the place of x, I'm putting y squared. All right. All right, so y squared, that's going to be y squared times y squared over, and that's going to be y squared squared plus y to the fourth. All right. And so this is going to be the limit. Now we're just in terms of y, as y goes to 0, and that's going to be y to the fourth. Now that's y to the fourth. Y to the fourth plus y to the fourth is 2y to the fourth, which is equal to the limit as y goes to 0 of 1/2. Oh, and look at that. That's 1/2. So the limit, we found limits that are different from two different paths. And so this limit does not exist. All right. All right. So that's, you know, we showed that the limit, we showed all three, or however many examples we worked, but all those limits that we worked, we showed they did not exist. And you can see it could get kind of messy, or not messy, but tedious, a lot of work to do that. I mean, look at all the work we did to show that that limit does not exist. All right. Now we got some properties of limits. So properties of limits, it says the limit of a sum is the sum of the limits. Okay, that's, you know, that was back when you were doing single variable calculus. And the limit of a difference is the difference of the limits. Okay, so if you got the limit of something minus something, or the limit of something plus something, then you can do the limit of the first term plus or minus the limit of the next term. Okay, and then the limit of a constant times a function is the constant times the limit of the function. And then the limit of a product is the product of the limits. And the limit of a quotient is the quotient of the limits. And of course, providing that the limit of the denominator is not 0. All right. And then we have these little special limits right here. The limit of x as xy goes to ab is a. Oh, well, that's just telling us we can take the a and plug it in for x. And same thing here, the limit of y, we can take the b and plug it in for y. And then the limit of a constant is just a constant. And then we've got the limit of a polynomial. Okay, so we know a polynomial is continuous, right? And so if we take the limit of some polynomial, p, as xy goes to ab, oh, this is telling us we can evaluate the polynomial at that point, and that'll give us the limit. And then the same thing with a quotient. If we have a quotient p of xy over r of xy, well, that's just equal. We can take the ab and plug it into the rational function, and of course, ab is in the domain of the rational function. ab has to be in the domain of it. All right, so let's just look at these two real quick. So these problems here, they should be pretty easy. Well, this is a polynomial. We know it's continuous everywhere, so we just plug the 1 in for x and the 2 in for y. And so that's going to give us 1 squared times 2 cubed minus 1 cubed times 2 squared plus 3 times 1 plus 2 times 2. And you do your arithmetic and you get 11. And then same thing for this one. Is it continuous at -2, 3? Well, we'll see in just a minute when we plug it in, won't we? If we get 0 in the denominator, then we know it's not. We won't be able to just plug the number in. And so we've got what? -2 squared times 3 plus 1 over -2 cubed times 3 squared minus 2 times -3. I'll plug all that in, right? Let's see. Make sure I didn't miss anything. Yeah, I did miss it, didn't I? That should be a negative. I don't know why I put -2. That should be -3. So that's -13 over 68 when you do the arithmetic. All right. All right. So what about this problem here? All right, so they're asking us to evaluate the limit. So notice if we plug 0 in, we will actually get 0 over 0. You see that? So we can't just plug the point in. And to save a little time for this video, I mean, we've worked several problems where we came in along the x-axis, the y-axis, the line y equal x, the lines y equal mx, and we even came along the parabola x equal y squared. Okay, and so to save a little time, I'm not going to go through and do all that again, but to let you know, if we go along the x-axis, the y-axis, y equal x squared, x equal y squared, and actually y equals x. If we did all of those, these limits are all 0. Okay? Those limits are all 0. So does that mean that that limit is equal to 0? Absolutely not. So what can we do here? Well, as I promised at the first of the video, we're going to use the definition. Okay? It's not fun. I doubt if anybody likes doing it like this, but we're going to do it. So before we get started, I'm going to go up and I'm going to copy that part that we need. Well, let's just go back up here to the top. All right. So it says let f be a function of two variables whose domain D includes points arbitrarily close to AB. Then we say that the limit of f of xy as xy approaches AB as L. We write this: if for every number epsilon there is a corresponding number delta greater than 0, such that if xy is in the domain and this is between 0 and delta, then f of xy, the absolute value, minus L is equal to epsilon. And you know something, now that I'm looking at this again, this all should be an absolute value. Sorry about that. All right, so I just making all kinds of mistakes writing my notes, whatnot, but we got it fixed, so it's okay. All right, so let's go by this, okay, what this tells us. So I'm going to let epsilon be greater than 0, and I want to find a delta. That's a delta. I know it looks sad, doesn't it? But that's delta greater than 0, such that if, okay, so what do we have here? We've got 0 is less than the square root. All right, so what is that? That's going to be x minus 0 squared plus y minus 0 squared is less than delta. Okay, that's what it tells us. And what's A and what's B? Well, A is 0, B is 0. Okay. All right. Then I have this part. I've got what? The absolute value of f of xy minus L. So f of xy, that's this 3x squared y over x squared plus y. So that's 3x squared y over x squared plus y squared minus 0 is less than epsilon. All right. So what does that give us? That gives us 0 less than the square root of x squared plus y squared is less than delta. Then I have 3x squared absolute value of y over x squared plus y squared is less than epsilon. All right. Well, hopefully you see where this came from that. Okay, x minus 0 is x. But what about this? Well, of course, this minus 0 leaves me with just the function. But what happened to the absolute value around the whole thing? Well, I don't need the absolute value around the whole thing because x squared, and y squared, they're all positive. Okay, because I'm squaring them. The only possibility of a negative is the y here. So I just need the absolute value on the y. All right, so let's think about some things. All right, so we have, now, what do we know? We know that x squared is less than or equal to x squared plus y squared, since y squared is greater than or equal to 0, right? We know that for a fact. If y squared is 0 or positive, then we know this is either equal to x squared or it's larger than x squared, right? So that would mean that what? X squared over x squared plus y squared is what? Less than or equal to 1. Now, where did that come from? All right, where did that come from? Well, I hope you can kind of see what we're trying to do. We're trying to, look at the function we have. We got this. See the x squared over x squared plus y squared, and hopefully you'll see as we move on in the problem. But do you understand? Do you see why this is less than or equal to 1? Because if this is either equal to x or larger than x, so that means the denominator is either equal to the numerator, and if that's the case, it equals 1, or it's larger than the numerator, then that means it's less than 1. Okay? So therefore, we've got 3x squared absolute value of y over x squared plus y squared is less than or equal to what? All right, so let's look at this for just a second. So do you see this part right here? That's either equal to 1 or less than 1. Right? So that means this is less than or equal to 3 times the absolute value of y. Okay? Because, think about it. If this is 1, then it's equal to that. If it's less than 1, then this over here is less than this. All right? And we know that this is equal to 3 times the square root of y squared. Right? That's equal to 3 times the square root of y squared, which we know this is less than or equal to 3 times what? See, there's the 3 and there's the 3, but we know that the square root of y squared, that would be less than or equal to the square root of x squared plus y squared. All right, so now let's choose our delta. So let's choose delta to equal epsilon over 3. And let's see what happens. So let's write let's write this down again. So that's going to be the absolute value of 3x squared y over x squared plus y squared minus 0. So all I did, I just wrote this down again. Now, what do we know? What do we know about this? We know this is less than or equal to what? Well, do you see this right here? This is less than or equal to this, right? So that's less than or equal to 3 times the square root of x squared plus y squared, which is less than or equal to 3 times what? Well, let's look at this. So we've got the 3 and the 3. We'll see the 3 and the 3. Those are the same. What is this less than or equal to? It's less than or equal to delta. You see that? So that's less than or equal to delta, which, what does that equal? That equals 3 times, and what did we choose delta to be? Epsilon over 3, which equals epsilon. And so that's what we needed to show. And so what was our limit? We used the point 0, 0. You see that? And isn't that what we chose, that we were testing our limit to see if it was 0? See the L here, 0? That's what we chose, L to be 0. And so that means that this limit here is equal to 0. And that's what I was telling you earlier, that using the definition, that's not really that fun. Okay, but I'm going to show you something in a minute, okay, where we're going to solve this thing. We're going to find the limit, but you can see how hard it is. You see how hard it is to show that one of these limits, show that limit exists. I mean, look at there. Look at here. All these paths here, they all equal 0, and so, but still with that, we could not say that limit goes to 0. We had to go through the definition here and show that it equals 0. Okay. All right. So let's look at this problem. Or let's look at the next thing, continuity. All right, so definition. A function f of 2 variables is called continuous at a, b if the limit of f of xy as xy goes to ab is equal to f of ab. So the limit of the function as x approaches ab has to equal the function evaluated at that point. And then we say that f is continuous on D if f is continuous at every point ab on D. All right, so let's look at this next example here. All right, so where is the function f of xy equal x squared minus y squared over x squared plus y squared continuous? Okay, so we know right off that f is discontinuous at 0, 0, right? Because if we plug 0, 0 in, we would get what? 0 over 0. But we also know f is a rational function. So it is continuous on its domain. All right. So it's continuous. It's actually continuous everywhere except for the point 0, 0. Is there anything that's going to make the numerator undefined or have some kind of restriction on the numerator? No, the numerator can be anything. And what about the denominator? Well, the denominator can be any number also, right? It can be any number also, except for 0. So the domain here is the set of all xy such that xy does not equal the point 0, 0. That would be the domain, and this function is continuous everywhere except for 0, 0. All right, so what about this one? Where is this one continuous, or where is it discontinuous? All right, so how about this one? Well, actually this function is actually defined at 0, 0 now, right? G is defined at 0, 0. So that would, see, if you notice, this is the same rational function as we had up here, right? So, and it wasn't defined at 0, 0, but now you see the piecewise function we have here. Now they're saying, oh, at the point 0, 0, this function g of xy is equal to 0. So it's defined there now. All right, but now what do we have to show? Well, remember, g of 0, 0 is equal to 0, right? That's what it's telling us. If we plug in 0, 0, we get 0 as an answer. And what does it say up here? It says, okay, we got 0 here. Now that's what the limit has to equal. So the limit, as xy goes to 0, 0 of g of xy is equal to the limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared. Well, what is that? That does not exist. And you might be sitting there thinking to yourself, well, how do you know it does not exist? Okay, so remember, x squared minus y squared over x squared plus y squared, and we're taking the limit as it goes to 0, 0. So let's come back up here. See, we already did that problem. That was the first example we worked. We did this limit, and we showed we got 1 and -1. That limit does not exist. See that? Let's see where. Keep going. Oh, here we go. All right, that does not exist. So this function, so g of xy is discontinuous at 0, 0. All right. All right, so now let's look at the next one. All right. So this problem here may look familiar to you. Well, this part of it, 3x squared y over x squared plus y squared. Remember earlier we just worked a problem where we did the limit of this as x goes to 0, 0. We used the definition, and we showed that the limit of this as xy goes to 0, 0 is equal to 0, right? And this function here, at 0, it's equal to 0. All right? All right, so I know that f of 0, 0, that's defined, that equals 0. And now I need to show that the limit exists, or need to show that the limit is equal to 0. Well, of course, we already know that it is, but I want to show you something I want to show you something different here. Okay, let's, that was not fun finding that limit. What we did up here. Let's just go back up here to remind you what we did. That's this problem right here. See, it's the same thing, and we went through all this. We went through the definition to show that that limit was 0. All right. Well, I don't want to do that again. And of course, I know we already know it's 0, but let's suppose we didn't. So let's find the limit as xy goes to 0, 0 of 3x squared y over x squared plus y squared. All right. All right. So how in the world are we going to work this problem? Well, let's look at this. Let's do it using polar coordinates. Remember polar coordinates where x is equal to r cosine theta, y is equal to r sine theta, and r squared is equal to x squared plus y squared. Okay. All right. So let's find this limit. So this is going to be the limit. Now I'm switching to polar coordinates, so that's going to be r theta goes to 0 theta. Theta is going to be theta. R is going to 0. Okay. Now let's look at this. That's 3. Now what's x? X is r cosine theta. So if we take r cosine theta and plug it in for x, that's going to give us r squared cosine squared, right? And then I'm going to take r sine theta and plug it in for y. So that's times r sine theta. And then look at this, over x squared plus y squared. Well, what's x squared plus y squared? It is r squared. And so this is going to give me the limit as r theta goes to 0 theta. Now let's look and see what we can do here. So see how this r squared and this r squared cancels out? That's going to leave us with 3r cosine squared theta sine theta, right? And that is just equal to what? Well, r is going to 0, so that's 0 times whatever that is just 0. You see that? And so that's our limit. Okay, so you can switch to polar coordinates, and you just take the limit as r theta goes to the 0 theta. And so let's not get away from what the problem was asking. So that means f of xy is continuous on R2. All right. And I'm gonna do some more problems in I'll do another problem in polar coordinates, okay, to show you. All right, but let's look at this one. We've got, where is the function h of xy equal negative x squared plus y squared continuous? All right, so, well, let's just look at the numerator, because that's where the variables are. Well, we know x squared plus y squared, that is a polynomial, and it's continuous on R2. Polynomial is. Now, so x squared plus y squared, whatever we plug in there, we'll get whatever number. Okay? So, you know, if we have, let's just say we got e to the negative t. Okay? Let's replace the x squared plus y squared with t. This x squared plus y squared with t. Just look at that single variable. So, is there a number that we can plug in for t that makes it undefined, violates some kind of math law or something like that? No. We can raise e to any power. It doesn't matter what it is. Okay? So we know, that kind of moved over. So we know this is continuous for all values of t. So we know that h of x, y, which is equal to e to the negative x squared plus y squared. I mean, we just show, we know here that exponent can be anything. So it doesn't matter what this is. This exponent, this entire exponent can be anything. And we know x squared plus y squared, it's continuous everywhere. It can be anything, but it's a polynomial. So we know this is continuous on R2. All right, so that was maybe the last example, but I've got two more. Just, we're not even to an hour yet, so just hang in there for a little bit longer. We're almost done. All right, let's do another example. So we want to evaluate the limit as xy goes to 0, 0, sine x squared plus y squared over x squared plus y squared. Okay. So we've got the limit as xy goes to 0, 0, sine x squared plus y squared over x squared plus y squared equals the limit as r theta goes to 0 theta. Okay, I'm going to use polar coordinates. All right, so that's going to be the sine of what? What's x squared plus y squared? That's r squared over, and what's x squared plus y squared? That's r squared. So now we have to evaluate this limit, and this is actually a limit. It's just in terms of r now. So I've got sine r squared over r squared. Now how do we calculate that? Because let's see, if we plug in 0, that's going to give us 0 over 0. Okay. But we're in one variable now. We're just in terms of r. So I can use, do you remember? We can use L'Hopital's rule. So this is the limit as r goes to 0 of, what is that? Cosine r squared times 2r over 2r. And look at that. Man, that worked out nice, didn't it? And that's equal to the limit as r goes to 0 of cosine r squared, which is cosine 0 squared, which is 1. And so that limit's 1. So when you can use polar coordinates, I would do that. Okay, use the polar coordinates when you can. All right, so now let's look at this. We've got another example, and this is the last one. And look, if you've watched this long, just stay on here and finish watching it. So we want to evaluate the limit as x, y, z goes to 0, 0, 0. All right, so how how fun is this going to be? So function of 3 variables. And that's going to be x squared plus y squared minus z squared over x squared plus y squared plus z squared. All right, so how in the world do we work something like this? Well, we work it like we worked the other problems. All right, so if you look at this, let's just come over here and so this is the point we're coming into. So what if we came in along the x-axis? We can come in along the y-axis. We can come in along the z-axis. See that? So let's look at this. How about along the x-axis? So along the x-axis, that's going to mean what? Y and z are both 0, right? If we're on this axis, y is 0 and z is 0. And so that's going to give us the limit as x 0, 0 goes to 0, 0, 0 of what? X squared plus 0 squared minus 0 squared over x squared plus 0 squared plus 0 squared, which that's the limit as x goes to 0. We're just in terms of x now, of x squared over x squared, which is the limit as x goes to 0 of 1, which that's 1. Okay? And I guess I should have wrote the directions a little different. I guess I didn't really mean to write evaluate, but does it exist? Or actually show that it doesn't exist, because it doesn't, but let's go through it and work it. All right, and then what about along the y-axis? All right, so here's our rational function there. So that's going to be the limit 0, y, 0 goes to 0, 0, 0. Because remember, here along the y-axis, x and z are both 0. All right. And so this is going to be 0 squared plus y squared minus 0 squared over 0 squared plus y squared plus 0 squared, which that's the limit as y goes to 0 of y squared over y squared, which is the limit as y goes to 0 of 1, which equals 1. So those are the same. All right. So now let's look at going along the z-axis, and I'm going to move this down here so we can see it. All right. So now let's look along the z-axis. So if we come along the z-axis here, that's going to be when x and y are both 0. So that's going to be the limit as 0, 0, z goes to 0, 0, 0. And that's going to be 0 squared plus 0 squared minus z squared over 0 squared plus y plus 0 squared plus z squared. You can probably see how this one's going to be different. This is going to be the limit as z goes to 0 of negative z squared over z squared, which is the limit as z goes to 0 of negative 1, which is negative 1. So we showed there those two limits are different. So this limit does not exist. And I believe that's all I've got for you in this video. I hope it helped. I hope it made sense. I mean, you know, these limits of these multivariable functions, they can get difficult, some of them. Remember, if you can, try polar coordinates. Come along different paths. And once you work them, once you work several of them and look at them, a lot of these limits when you're coming in from the x-axis, the y-axis, that kind of stuff, you can probably do it pretty quick in your head. But that's it. That's this video. I hope you enjoyed it. Go check out my other videos. Give me a like, share, and subscribe. And I'll see y'all in the next one. Later.